we are looking at standard error and confidence intervals for slope. So this guy is a blast from the past. This is the standard deviation of your residuals. I call it the average distance from the line. It's the standard deviation of your residuals. Notice you take your residuals squared, you add them up, you divide by n minus 2, and then you take a square root. Okay. And this is really trying to predict sigma, the true standard deviation spread around the line. Okay. I call this my typical prediction error. Okay. It's how off are my predictions on average. Okay. Typical prediction error. Okay. The standard deviation of your residuals. Okay. And we use that to say, okay, now we have the standard deviation of the residuals. We want to create a confidence interval for the slope beta. Okay, my best guess of beta is my sample slope, B. And then we need to do plus or minus T star, which is based on n minus 2 degrees of freedom. Okay, and we need to do the standard error, not of my residuals, but of my x's. Okay, of my slopes, the standard error of my slopes. All right. And the way that we calculate this, you never need to do it by hand. It's really the standard deviation of the residuals divided by the deviation of your x's squared, added up, all that good stuff. Okay. Which kind of makes sense. The residuals are your delta y's. See, delta y over delta x. So the residuals are your slope. This is kind of, if you think about it, delta y over, that's clearly delta x. And that's why that's the standard error of your slope. How far away are your y's on average? How far away are your x's on average? Okay. And T star is the critical value. So how hard is this? Well, if you are given a silver platter like this that we're used to seeing, okay, so this one they actually gave you the least squares regression line. You can see that the constant is your y-intercept. The cry count, this is for data on how much a baby cries and predicted IQ, okay? This is your slope, okay? And if you take those two, take your sort of equation, this stuff we get to just ignore, as you can see right there. We ignore that. We're not doing inference on the y-intercept, okay? We're doing inference on the slope. So this is S. This is the average distance from the line. So if I were to plug in an X value, then I would get, if I plugged in a cry count for a particular baby, I would get out a predicted IQ, and I'm going to be off on average by 17.5, okay? That's the standard deviation of the residuals. Now the standard error, the standard deviation of my slopes is this 0.4870, okay? And we get a test statistic literally by doing this slope divided by this standard deviation, okay? So this divided by this equals that, all right? This divided by this equals that. That's my test statistic. And this p-value is the probability that I would have a slope like this or greater when there's really no slope. Okay, so we're going to get to that p-value when we do a test. But notice, what do we need? We need our b. Well, this is our b right here. Okay, that's our b. So we put it in right there, 1.4929. We need a test statistic, which I can get from my table. If you look at this, we had, I think it was 38 pieces of data. And if we want a 95% confidence interval, we have to do 38 minus 2 would be 36. But there is no 36, so I'm going to just go over to 30. And at 95, we see 2.042 is my T star. So that's what we take right there. So there's the 2.042. And then my standard error is right here. And then I multiply and I do plus or minus. And now I could say we are 95% confident that the true slope, not my sample slope, but the true slope is between 0.4985 and 2.4873. Okay, so we're true that we're confident, 95% confident that beta is between those two values. Okay, so that is your confidence interval. All right, so good luck. we'll talk about hypothesis tests in the next one.